Hello, Khalil here. And what I'm working on right now is the EE138 lab project. It is the control systems project where you control a DC brush motor with an encoder, and you implement PID and some other features like position control as well as speed control. I have the oscilloscope hooked up here to a DAC pin from the 7021, and it outputs a voltage proportional to the RPMs of the motor. And I'll be showing that on the oscilloscope in a sec. So what I'm going to do right now is I'm going to lower the brightness, and I'm going to press number 1 to make the motor move to 1,500 RPMs. And right now it is moving up. It's kind of very difficult to see, but the display shows the exact RPMs. And if you look over here, I didn't really get a chance to see it. If I press 0, it'll decelerate down to 1. And then I can also punch in my own number. For example, if I put in let's say 2,000. And I think if I press the C button, yeah, that'll do it. That'll make it go negative, so I'll make it go the other way. So now it's going the opposite direction into 2,000 RPMs. And it's around about there. It's just oscillating around the center point, around the thresholds. Okay? So in moving to free RTOS, I actually have seen no performance problems after I fixed out some of the bugs that I had. I'm going to set this to 0, okay? And we can see that the display, the oscilloscope is back to normal. All right, everything is down to 0. Here are a couple of things that I changed in my move to free RTOS. I'll move up to the top. I've cleaned up the global namespace. I put a lot of the variables into tasks where they should be rather than having inside the global space. I set some variables as private variables within some functions, just using static. And removed unused variables. There are a lot of them. Using standard int for some of the variables. So when you define your variables, you use uint32 to specify that you want a unsigned integer 32-bit number, rather than just using unsigned bit and int to make it a little more explanatory. Move from if else else to a switch case where it was appropriate. Converted some of the code to inline functions to make it a little more optimal. And split functionality across tasks. So one of them I made And these are some examples of what I've done within the tasks themselves. I also gave a descriptive name to a lot of the variables and eliminated a lot of the magic numbers that were in the code, but not all of them. A lot of them are not there. And I kind of went a little harder and also commented a lot of the code here. Okay. Here are all the global variables. We have this thing called digit, which is actually a shared resource that's actually going to be protected by this mutex here, the X display structure mutex. So I have some free RTOS primitives such as this mutex. I also have a display mutex that actually keeps and makes sure that when I am displaying idle acceleration or deceleration, like in this case here, now it's accelerating. And if I put in deceleration, the display holding down and keep the display right now is that mutex is actually keeping the display so it only shows letters rather than showing the numbers. This will actually give the mutex and give it back so that we only see numbers here. Then we also have a keyboard cue. So every single time I press on the keypad, anytime I make any press on the keypad, it'll send an item onto the queue, and then the keypad processing task will take it and then it'll actually do something with it. Okay. Actually, I'm going to scroll up a little bit, and I'm just going to explain that we have a couple of tasks here. We have the V handle keypad, which is a rapidly firing task that is actually polling for the keypad. We have a update 7-segment display. This is actually an idle task, but whenever the CPU is idle, it tries to update the display. We have the PID controller, which controls the motor. We have the display controller, which actually decides what things to show on the display. And then we also have a DAC controller, just to create the output voltages proportional to RPM. Then finally, we have a process keyboard, which is the consumer of cue items from the handle keypad. There's a lot of code that happens inside of the process keyboard, which is the reason why I didn't put all that inside of the handle keypad. If you scroll down, we can see all the priorities. So PID is critical. Update 7-segment is idle. Process keyboard is low. DAC controller is medium. I just want to make sure it pops out. I want to be able to see the debug messages. Display controller is low, and the handle keypad is actually quite high. This is to make sure that we're getting each one of those key presses. And then we start the scheduler. And then this is just the rest of the code, which will be made available to the people who are concerned. And yeah, so this is basically all the code ported over to FreeRTOS and also optimized as well and organized into logical tasks for the class. Beyond going just for using like 1 or 2 timers, now you can have up to n many tasks all set up in one timer, which makes making code and organizing code really useful. Okay, so with that, I think I'm nearly done with my project. The next thing is to create the documentation, and I think we're good.